let's learn about the ratio and root tests. So it's two tests, so let me go through them real quick. For the ratio test, we have this number that we're going to call L, and it's the limit as n goes to infinity. I do the absolute value of a sub n plus 1 over a sub n. And if that limit exists, we're going to call it L. If the limit doesn't exist, then you just can't use this test, really. This is going to include the possibility that L could be infinity. So that's allowed here. So L doesn't have to be a finite number. It could be infinity, but it can't be a limit that just doesn't exist. So if that's the case, then if L is less than 1, then our series is convergent, and more specifically, it's absolutely convergent, if you care about that. But so it's convergent. And if L is bigger than 1, then this series is divergent, and this includes the case when L is infinity. We consider L to be greater than 1 if this limit happens to be infinity. Unfortunately, if L is exactly 1, then the test does not tell us anything. The test is just inconclusive. So we'll see some examples, but first let me run through the root test. The root test is sort of similar to the ratio test. We're still going to have this number L. It's something a bit different. It's the limit as n goes to infinity of this. It's like the nth root of the absolute value of a sub n. And again, this could be infinity, so we're going to include the possibility that L is infinity. If the limit doesn't exist, then you just can't use this test. So we get some L, hopefully. And then we interpret the results. I was kind of lazy, but you interpret the result the exact same way as the ratio test. It's just a different L, but if this L is less than 1, then the series is absolutely convergent. If this L is greater than 1, then the series is divergent. And if L equals 1, then the root test is inconclusive. I just didn't want to write all that again. So you interpret the result the same way you interpret the ratio test. It's just a different L. Okay, so let's see an example. And actually, if you were in my class, we did this example recently. We did it with the integral test, and it took us kind of a lot of work. We had to, first of all, we had to justify that you can use the integral test. Then that means that we have to do the integral, like the improper integral of x e to the negative x, which requires integration by parts and L'Hopital's rule, and it was quite a bit of work. So let's look at the same series again, and we're going to be able to conclude really quickly what this does using the ratio test now that we know it. Let's find L. So L, I do the limit as n goes to infinity. There's an absolute value. I'm going to do a sub n plus 1. So it's like I take this, but I'm replacing n's with n. Whoops. I am replacing n's with n plus 1s, so that's a sub n plus 1. And notice I used parentheses here because this is actually going to turn into negative n minus 1. So sometimes these parentheses are important. Anyway, on the bottom of this fraction is just a sub n, so I just copy this down. Okay, now we have a limit to find. Okay, what are we doing here? So first of all, I don't think these absolute values are actually doing anything. So I'm going to drop these absolute values. N is going to positive infinity, so everything I see in here is a positive number, keeping in mind that e to any power, even a negative power, is a positive number. So what's inside these absolute values is already positive, so I'm just going to drop them. What else do I have? I've got So let me not go too fast. Like I said, this is minus n minus 1. So maybe I won't even do that much this step. I just dropped the absolute values and I distributed this negative sign. I'm going to cancel some e to the n, like I've got a power of e and another power of e, so I can subtract these. In fact, I can just cancel an e to the negative n, so that there's still e to the negative 1 left over. And as a matter of fact, I think I can just look at this and tell what the limit is. So e to the negative 1, okay, let me write this. Just clean it up a little bit. I'm not doing too much right now. Because this turned into e to the negative 1. And then I look at the rest of it, and this is going to 1. And e to the negative 1 is a constant, so this is like, yeah, I'm probably over-explaining at this point, but we get our limit. So that is our L, e to the negative 1. And that is a number that's less than 1. I don't need to know too much about the number e to know that. E is about 2.7 something something, so e to the negative 1 is like 1 over 2.7 something something. You don't need to know the exact value of e, and it goes on forever, but it's easy enough to see that that's less than 1. We don't need a calculator or anything. So the original series is absolutely convergent. We weren't really asked that, so I'll just say convergent. And that was not nearly as much work as it takes to investigate this using the integral test. Okay. Let's do another one. So on this one, we will be asked whether a series is absolutely convergent, conditionally convergent, or divergent. And this is going to bring back something that we barely talked about, but we did talk about it recently. N factorial. So I'm going to use the ratio test again. I'm eventually going to show you an example with the root test, but let's use the ratio test again. I'm also going to explain when do you use the ratio test and when do you use the root test. But for now, let's just go ratio test. So I need to do this, right? So here's my a sub n plus 1. Oops. Of course, that's n plus 1 factorial. And then here's my a sub n. Sort of like that. Okay, now I'm not going to drop these absolute values, at least not right away. I'm afraid that I see some negative numbers in here. So let me be careful about that. I'll keep the absolute values. What I am going to do is I'm going to flip the fraction, of course. Okay, now there's some easy cancellation to see. I've got a negative 2 to the n, and basically I can cancel like negative 2 to the n. Here, I'll just cross this off because there's a negative 2 to the 1 left over. Now, let me explain to you what else is about to happen. There's going to be some cancellation between the n factorial and the n plus 1 factorial. So I'm going to set that up. So these negative 2's are gone, except I have a negative 2 to the 1 left over. So I guess there's nothing left over on the bottom of this fraction, so I'll just put a 1 there. So this is the first time doing this, so let me go slow here. Here's one way of, here's what I'll do. What is n plus 1 factorial? That's n plus 1 times n minus 1 all the way down until we hit 1. And then what is n factorial? That's n times n minus 1 all the way down until we hit 1. All of this from n all the way down to 1 cancels all of this. And the n plus 1 is still left there. So I'm left with that. And of course, well, yeah, maybe I could get rid of the absolute values and call this a plus 2. But actually, let's just jump straight to the answer. N's going to infinity, so this goes to 0. And the absolute value of 0 is 0, so let's just say 0. Okay, so that's our L. It is less than 1. So the series is absolutely convergent. All right. Let me do one more example with the ratio test. We're going to try the ratio test on this series and see what it tells us. So my L, done this a few times now. I'm going to do the limit as n goes to infinity of this fraction on, maybe I'll do the easy part first. On the bottom of the fraction, it's just a sub n. I just copy this down. On the top of this fraction, I do a sub n plus 1. So if I put in n plus 1 here, this turns into the square root of n plus 2, right? And if I put n plus 1 in here, I get n plus 1 squared plus 3. Okay, let's find this limit. I don't see any negative numbers inside of here. I don't see anything that would be negative. Like, I only see, especially considering n's going to positive infinity, if that helps. So these absolute values really aren't doing anything in this case. So let me drop them. And of course, flip the fraction. So this is square root of n plus 2. Maybe actually I'll expand this. So this is n squared plus 2n plus 1 plus 3 times the reciprocal of this. So n squared plus 3 over n plus 1, like that. Okay, now this is, you know, I could like just multiply across and this would be an infinity over infinity form, but I don't think I really want to use L'Hopital's rule. I think I just want to like algebraically figure this out. So maybe here's a slick way to do it. Let me take the stuff that has a square root on it, like I've got this and this, and I can put one square root over the whole thing, like that, times, and then the stuff without a square root on it, n squared plus 3 over n squared plus 2n plus, let's say, 4. And this sets me up to use a rule that we're very comfortable with by now. If you have a polynomial over another polynomial, you can just look at what the leading terms are doing. Underneath this square root, I have a polynomial over a polynomial, and they have the same leading term. It's n and n. So I'm comfortable saying this goes to 1. Likewise, over here, I've got another polynomial over a polynomial, and they have the same leading term. So I'm going to say this goes to 1. So this is, this is under a square root. And this isn't. Of course, square root of 1 is just 1, and 1 times 1 is 1. So we get 1. So, unfortunately, this is what we don't like. When L is exactly 1, the ratio test is inconclusive. This is one of those things when you're investigating a series that, so sometimes it's hard to see this coming, but basically we just wasted our time. I guess we learned something, but we didn't learn the answer to our question. Like if we were wondering whether this series converges or diverges, we still don't know. All we know is that the ratio test doesn't tell us anything, and we should try something else. So let me just real quick. I'm not gonna actually show all the work for this, but let me tell you what does work. Something that we already learned. This looks like it's going to be susceptible to the limit comparison test. For the limit comparison test, you have an a sub n and a b sub n. I always make a sub n the original terms of the series that I'm trying to investigate. Oops, sorry. N squared plus 3. And my b sub n is like what I get if I look at a sub n and I ignore all of the less important parts. So for my b sub n, I would ignore the 1 and just call this square root of n. And on the bottom, I would ignore the 3 and just put the n squared on the bottom. So this is 1 over n to the 3 halves. So I'm not showing all the work. Of course, to use the limit comparison test, you have to do the limit of this over this and get a finite answer. But if you show that work, you will get a finite answer, a positive finite answer, I should say, sorry. So I'm skipping that work, but that would tell you, since b sub n is a p-series with p equals 3 halves, if you do the work that I'm skipping, that this would tell you that the series that we're investigating converges, because b sub n, the series with b sub n definitely converges because it's a p-series. But yeah, again, I'm skipping the work. Okay, so what did we learn? We saw examples of this at least. What is the ratio test good for? I would say it's good when you have like a constant to the nth power, like 2 to the n or 3 to the n. It could be something to the negative n or the 2n or something like that. So it could be like our first example had an e to the negative n on it. What else is it good for? It's good for factorials. We saw an example of that. So it could be n factorial or like 2n plus 1 factorial or something like that. What is it not good for? And when I say not good, I mean it's going to be inconclusive. It's going to ultimately be a waste of time. Like the last one, I would say that the reason why, in retrospect, the reason why we maybe could have foreseen that the ratio test is going to be a waste of time on this is because this, roughly speaking, it only involves powers of n. There's nothing exponential. There's nothing with n in the power, like 2 to the n or anything like that. There's also no factorials. There's just powers and roots. In general, the ratio test is not good if that's what you're looking at. Of course, if you see any of this stuff up here, that's an exception. But if I don't see anything exponential and I don't see any factorials, and the only things that I see are like powers of n, including roots like square root of n, etc., and also including logarithms. Roughly speaking, we're talking about slow-growing functions here. Polynomials don't grow very fast. Logarithms grow even slower than polynomials. Up here, this is like faster growth. So, yeah, the ratio test is not going to be so good for these things down here, or it will be inconclusive unless you see some of this stuff up there. Finally, because I promised I would actually get to the root test, really, I'm going to say that the ratio test is kind of the winner between the two tests. There are situations where you could use either one. So, like the root test could work for like these things, but the ratio test is so much more useful that I kind of jump to that. The one time where I would use the root test if you have a non-constant raised to the nth power, like something like this. This is not a constant. When I say a constant, I mean like 2 or 3 or a half or something. Not something that depends on n. So here we have something that depends on n and it's raised to the n. That's pretty much the one time that I would jump to the root test, is when I see something like that. So let's do an example. I'm going to do that exact example. We use the root test. So L is this thing. The limit n goes to infinity, nth root, absolute value, like that. Okay, so the first thing I always do is I look for an excuse to get rid of the absolute values, and this is going to be a positive number. N's going to positive infinity, so when n is some large positive number, this fraction is definitely positive. I raise it to the n, that's still going to be positive. These absolute values aren't doing anything. There's a positive number in there anyway. Now, here's the reason why I like the root test when we have something to the nth power, is the nth root of something to the nth power, basically I cancel the root with the power. So what do I mean? I mean those are gone. I'm just left with that. And that turns this into a very easy limit to find. It's a polynomial over polynomial. I just look at the leading terms. So it's like n over 3n. Like in my mind, I'm just covering up this. So 1/3. And how do we interpret this? We do the same thing we would do in the ratio test. Once we find L, I guess on all the examples I did, I think L turned out to be less than 1. But whatever L is, well, in any case, L was less than 1 again, so the series converges. We could also say it's absolutely convergent if we wanted to, but I guess we weren't asked.